So I'd now like to welcome Harry Kroto to come up and give the 2012 Sweeny lecture.
Well, he still looks like 2 years old to me, so it's, when you get to a certain age, everybody looks very much younger. But anyway, it's a pleasure to be here and obviously learn something about this historical sort of place. My wife made me put this on, but she knows it doesn't stay on very long because anyway, but it is a pleasure to be here and hopefully talk to you something about the things that are interesting to me, and thank you very much for the invitation. So it's going to be carbon in nano and outer space. Well, that's not very loud. I think I want it louder than that. Okay. Occasionally I'll wake you up that way. All right, so how did I become a scientist? And I thought I'd go back to, because there's some young people here, to tell you that I actually was quite young once, believe it or not. And as a kid I didn't even know what a scientist was. I really wanted to be Superman. And here's the proof, okay. Anyway, you know, flying was slightly difficult, so I had to do something else like play tennis and gymnastics. And at school, I think it's very important that whilst you're at university, young people here should realize you must do as many things as you possibly can. You know, it will be the last time when you have easy ways to explore other aspects of your creative potential. At school, I acted in the play Henry V, and I take this picture and blow this up. I'm the handsome guy on the right, just in case you don't remember, realize. And I usually tell young people that you really should do science, because the guy in front, he decided to continue being an actor, and he's now 5,000 years old. And I'm quite young by comparison, really. And actually, Ian and I were in the same year at school. Fantastic actor, and in fact, he stayed with us a couple of years ago and did a fantastic one-man show with the kids at Florida State, and also did a workshop on Shakespeare sonnets. He's the greatest Shakespearean actor, greatest actor of my generation, and it's really a shame that you only see him as Gandalf or Magneto, because he's one of the great actors. If you're a Brit, you would realize that. But in fact, my main interest in many ways is graphic art, and it's very important to realize that you must actually keep on with those things, and these are some things I did at school and actually at university. And in fact, these are posters at Sheffield. That was on the London Underground, and that was another poster on the Underground as well. I was art editor for the university magazine. This is the student magazine. So those are some designs. This got into a professional, international annual graphic design. It was the University of Sussex, and you see, these were all the departments, university departments that did chemistry, but we were the only one who lit the Bunsen burner, so it gives you an idea. It really did piss off a few people, that one, I must admit, in other universities. Anyway, so these are that's my book. My first award was not for science, it was actually for this design, which got me a national award in the Sunday Times before Rupert Murdoch actually bought it and screwed it all up. But anyway, here, and I used to look like this. Now, you youngsters are young and beautiful now, but you're going to look old and decrepit like me one day, so I enjoy your youth and beauty whilst you may. It will not actually continue. So these are some of the things I did, and I'm not quite sure what that was, but there you go. Margaret's in the front row here, and these are sort of a lot of things like this. And I do logos now. A lot of logos. That was for basically a buckyball workshop for children down under in Australia. Breakthrough. I always wish that G was a C, because then you go ouch as that arrow hits the center of this. This is Association Française Tallahassee, where I've got the French flag in there. I always like to have some designs. Oh, I redesigned the Japanese flag, as you can see there. And this stamp I designed for the UK in the centenary of the Nobel Prize. And this is my most recent one. I'm a very devout Jefferson, Madison, Thomas Paine, Benjamin Franklin guy. I think you had some of the most fantastic people who created this country, and it worries me now that that great secular, intelligent recognition of the importance of separation in church and state may well fold. It's a danger, I think. Oh, I designed this. someone's got to fight, even if you're a Brit, to fight for some of the most important things here. I designed this. This is Darwin's first design for a phylogenetic tree. It's a secret society, so if you want that design, just go to my website. Now, the reason that I sort of ended up as a scientist is that when I did this for biology class, I only got good for it. And I thought I should have got very good. But anyway, I ended up as a scientist. Okay. Oh, here's Ian back at Tallahassee taking this workshop with some young people in the drama school. I also had Meccano. Meccano was invented in the UK in 1901 and then stolen by I forget what his name was, but an American in 1913 and called erector set. And he moved the holes a millimeter to one side so he could get the patent for it. But anyway, give you an idea of advertisements in those days when I was a kid. Meccano boys, and I suppose we've got to add girls nowadays, and girls, are keen, ambitious, and inventive. No boy or girl who follows the Meccano hobby can be a bad boy or bad girl. Okay, and so here it's very important to recognize that erector set and Meccano was something more than a toy. It was very important. It's more than Lego. It's something very basic to the way that our world in engineering and technology is put together. And in fact, these are the sorts of things that my world was put together with nuts and bolts when I was a kid, and now my world is put together with electrons and atoms. And I use them today. The other thing I had was a camera. And I think I want to show you this because it epitomizes then and now. This was my camera, a Forklander, and I thought I'd show you how I used to take a picture. You know, you had to have bloody good incentive to do all that to get a picture and a photograph, right? How many of you went through that process? See, everybody over the age of 502. Now, it turns out that I had a very strong incentive, and she's in the front row here. And in fact, today, that's all you need to do. Now, you've lost a lot, because you don't know what's going on. You've got the pictures, but you're losing touch with the technology that we're using. And I think that's the big problem in the last 20 or 30 years. I knew everything about my camera. I knew it developed chemistry, I understood the light, I had the reciprocal, the F numbers and speed and things of this nature. And I think it's one of the problems that we face today. Anyway, I got interested in this molecule called benzene, okay? At school. And when I got to university, I got trained from organic chemistry, and I was fascinated by quantum mechanics and spectroscopy, and in particular, the fact that numbers commute, but in the quantum world, sometimes A times B is not equal to B times A. And if you want to understand spectroscopy, you have to understand quantum mechanics. It's not difficult. It's quite relatively easy, actually. If you want to understand why this is colored like this and what is going on, you're looking at photons which are interacting with the retina, and they involve that sort of equation. And in fact, the particular paper that's one of my favorites by Van Vleck, and it's this statement here, which I love very much. Practically everyone knows that the components of total angular momentum of the molecule relative to x, y, z fixed in space satisfy this commutation relationship. Now, I must admit, when we arrived at Newark Airport, I went along and asked a lot of people whether they actually knew this particular equation. Not a lot did, actually. So Van Vleck sort of seems that practically everyone knows that. So that was an interesting thing. But in fact, it's fundamental to quantum mechanics. And really consider this, and I think this is one of the things that made me into a scientist. Consider the numbers 1, 3, and 5. Okay? There we throw away the numbers and put in the blocks. And it was really quite a revelation to me that basically classical mechanics, we have the Earth orbiting the Sun, and in quantum mechanics, we have an electron orbiting a nucleus, and therefore angular momentum is involved, and it's quantized, J is 0, 1, 2, 3, and 4, And if you want to understand what's going on in your mobile phone and all the other digital things, you really do have to understand a bit about quantum mechanics. It's not very difficult maths, and it's not hard. It just needs effort. And anyway, for a given j, there are 2j plus 1 orientations of this spin, okay? When j is 0, 2j plus 1 is 1. When j is 1, 2j plus 1 is 3. When j is 2, 2j plus 1 is 5. Hence, 1, 3, and 5, okay? I'll throw away the numbers just in case there's some physicists who don't like numbers. You know, they're not very good. Anyway, let's double that, and double that, and double that. Move this to there, and that to there. Double this set, double that, double this. Move that to there, and this to there. And what have we got? The periodic table. Based on the numbers 1, 3, and 5. It's incredible. It explains the whole of chemistry, all of life, okay, and all the useful bits of physics, if any, okay. Of course, you know, physicists are arrogant. We're the master of the universe, and in fact that's true because physics is the overarching science of the way the universe works. But chemistry is that massive bit of physics, effectively, that pertains to us, physically, chemistry, biology, and things of this nature. And I think that's important, and it's based on the numbers 1, 3, and 5. And I think that's amazing that this simple set of numbers underpins the periodic table. And to some extent, I think it epitomizes what science is about. Now, when I started research, I was interested in the double bond rule. And it said that carbon doesn't multiple bond to second and third row atoms. Well, what's that then? I mean, OCS was well known. And so I was doing molecular spectroscopy as my PhD, and I got fascinated in trying to solve this problem. And we started to make some carbon-sulfur double bonds, and we made all those. In fact, it was relatively simple, that there were sulfur analogs of almost all the carbonyls you could look at. And then I worked on phosphorus. And in fact, I'll just go on. We were able to show that by rotations of molecules, we could detect the spectra of all these molecules, okay? Those are the phosphor alkenes. And we were the first people to make carbon-phosphorus double bonds. And I do consider that to be my greatest intellectual because I thought we must be able to do this. And in the case of C60, which of course is well known, it was a total accident. We did the right experiment at the right time, and we worked out what might be happening. But this one, I'm most fond of actually making this molecule, the first member of the phosphoralkene family. But we went on to make the triple bonded species, the phosphorus analog of the nitriles and the cyanides. And that was an exciting period as well. We made boron sulfides and detected them by microwave spectroscopy, okay? Now, the key breakthrough for this particular section of the talk was these two molecules, and they were made with David Walton, the phosphorus compounds with John Nixon. And this is the molecule that was really the start of it all. And this was made with David Walton, who was an expert at stringing carbon. He made a string of 32 carbon atoms. Fantastic, a linear chain of 32 carbon atoms. It did have benzene rings on them, or silyl groups on the end, but nevertheless I was really excited, and we decided to use this particular process, which is a copper catalyzed oxidative coupling reaction, to take the hydrogens out and string the carbon atoms together. And we worked with a student, an undergraduate student, Anthony Alexander, and made that molecule at the bottom, which is this one here. This, at the same time, radio astronomy was coming on song, and it was a tremendous development during the late 60s and early 70s. And we used this telescope, which was in Canada, because I've been at the National Research Council, and most of you who've ever been to Canada will realize this is a typical summer's day in Canada. And we used this particular telescope, and we were able to show by microwave spectroscopy, as it rotates, it has a dipole moment, gives out a photon, and you can detect the frequency of rotation, and you can show that there are carbon chain molecules. And we were able to show that all these molecules were in clouds, in some clouds, in interstellar space. Okay, and here's a picture. I used to have some hair, just to convince you that I once had some hair over there. This is, if you didn't recognize me, here. And here are my colleagues, Takeshi Oka, Lorne Avery, Norm Broughton, and John McLeod, at the National Research Council, when we were quite excited. And it got into the newspaper, and the newspaper said, the chemicals were discovered thanks to Canadian work in radio astrology, okay? And research by the Sussex team, okay, so that is the newspapers for you. About the same time as we detected this, infrared stars were detected, such as this one. Now, this is an infrared star really, it's quite bright, but you can't actually see it. This is forward scattering, like the sun. You're not actually seeing the star at all. This is forward scattering by dust around it. This is a massive thing. This is about the size of the solar system, and this is carbonaceous dust around this particular star. And it's this star which was interesting to me because our carbon chains were detected in this. And the idea that I had when I visited Rick Smalley in Rice University in 1984 was to try to understand the chemistry in that star. So what was that? Well, it was a relatively simple idea. Rick had developed this amazing technique which had revolutionized cluster science. Before this, the only thing you could see, say with iron or a refractory material, was a diatomic molecule, Fe2, or aluminium-2. But what Rick did is he vaporized this into helium and produced clusters of iron 20, 21, 22, and things of this nature. Now, I'd been invited by Bob Curl, and Bob said I should go and see Rick. And whilst I was visiting, I was looking at Rick, and Rick was a very ebullient character, and he was jumping all over the apparatus, excited about what he'd just been able to achieve in that year. And he was looking at aluminium clusters and silicon carbide clusters. And whilst he was jumping around, I thought, well, if we use a laser to vaporize this aluminium or silicon carbide, why not change this for graphite and produce the carbon chains and simulate the conditions in this star? That was the idea behind it. Very simple, straightforward experiment. I was pretty sure I knew what the result would be. Well, about 16, 17 months later, I got a phone call from Bob. He said, we're going to do this experiment. And with Jim Heath, Sean O'Brien, Yuan Liu, we actually did this experiment. And what, as many of you know, the mass spectrum showed a fantastically strong signal for C60+. Now, this is the mass spectrum. Okay, this is 11, 12, 13, 14, 15 carbon atoms. This is 10. And here we see an interesting pattern, which is possibly understood. But here, this was new, that we could make this. You see it's topped, it's actually off scale here. And I wrote on my printout, okay, C60+ question mark, okay, C60 huge and C70 as well, what was going on. Now, when we were when I was at Bell Labs in the 60s for a year, Margaret and I went up to see her cousin in Montreal, and we visited Expo 67, and this was the Expo 67 US Pavilion. And it was a spectacular building. And what you notice, I think you can see, is that it looks like it's all hexagons. You see that? I don't know whether you can see this. And somehow Buckminster Fuller had taken a sheet of hexagon and closed it into a cage. So this particular picture, which was in a magazine called Graphis, which I had got, this image was in my mind when we were discussing what might have happened and whether Buckminster Fuller had worked out how to close a flat sheet of graphite into that. I also had a star dome, which had back home in England, and because I'd just zipped over for a few days to do this experiment. But I sort of also remembered that this star dome had not only hexagons, but also pentagons. And we discussed this as we had a dinner, excited and stuff like this. And Rick, that night, cut out hexagons and to try to make this model, or a model, and then remember that it had pentagons. And when he put the pentagons, it magically closed up into this beautiful little ball with 60 atoms. And then we realized it was a soccer ball. It had to be right. I mean, you know, it's got to be right. Okay. And here's Jonathan Hare adjusting the gap. We were trying to repeat these experiments in England using a vapor. He put on my desk on a Monday this red solution, trying to extract it and prove this. There's a lot we went in the previous few years. That was on a Monday. And then Don Huffman and Volkan Kretschmer, they did some work, and they did a beautiful piece of work which you should really look into. Okay, so it was turned out that these two produced a paper, and it was sent to me to review, and it said it's got a red solution. I had a red solution on my desk, and I was looking at this. This is bad news. All right, shall I go for lunch or commit suicide? Thinking, I don't know what the food's like here, but eating Sussex is not a lot of difference between having lunch there and committing suicide. But anyway, I really do recommend that you look into the story, because these guys did a brilliant piece of science, brilliant piece of chemistry, even though they're physicists. But what we did was when, at the same time, we'd actually almost extracted it simultaneously, we were looking for the single line NMR spectrum of soot. And it was sent to Tony Avent, and he said, look, come down, I've got this fantastic single line for you. he says, there's only one problem with this line. It's this one. This is actually benzene. But what about this guy? And that miserable little line is the first NMR spectrum of C60. All right? It's beautiful. It's so small, but in fact, just showed this particular line was able to prove that C60, that all the carbon atoms were equivalent in C60. And I don't think there will ever, I doubt there will be another molecule with more than 60 atoms, I don't think it's possible, where you'll be able to prove the structure by one single line NMR spectrum, even for organic chemists. Okay, so there it is, and it was separated into two solutions, and here is the Sussex team, Ala Abdul Sadar, John Hare, Roger Taylor, and David Walton, where we actually were able to extract that molecule. Okay, so that's the story of C60. Oh, came from left field. I think it's very important in these days of difficult problems to realize that some of the big changes come from left field. If, for instance, you say, well, what have we done? Well, probably our major contribution is to organic chemistry. But it was not through organic chemistry. It was through microwave spectroscopy, radio astronomy, cluster science, which accidentally turned up the C60 molecule. And I think we have to fight for fundamental science to be a very broad spectrum. But one problem is that as money gets tight, people say, we've got to solve this problem, so there's got to be a solution in this area. It's not. It's probably some of the big breakthroughs are going to come from totally unexpected directions. And if we don't continue to give young people the chance to continue to do research in what they are interested in, rather than what we are interested in, we shall, I think, lose out in the long term. Anyway, the C60 breakthrough probably was a major contribution to organic chemistry, if nothing else. And in fact, there are now about 1,000 papers a year, or more than 1,000 papers a year, in fullerene science. This is actually the nanotubes, and this is actually graphene, which is rocketing up. I'm going to run on because I want to show some other things about what is nanotechnology. Well, let's think about genetic engineering. Genetic engineering by human beings. People think it's new, okay? But look at this. This animal has been re-engineered into a chihuahua, okay? All right? Without any knowledge of DNA, okay? It's interesting. With DNA, we could probably do it in one step. In fact, we could probably re-engineer a human being into a chihuahua by messing around with the DNA. And there are some of them who've got the brains of chihuahuas that we should do that, particularly politicians, it seems to me. And so if we think about what nanotechnology is, it's atom by atom, molecule by molecule assembly of a complex and/or functional system. By that definition, we are the results of science and nanotechnology. We have been engineered polymer by polymer, protein by protein, into a complex system. We've been built up from bottom-up assembly. And that shows you that there is a massive future for nanotechnology. So anyway, as you heard, I sort of ended up at FSU, and I had to retire, and I thought I'd show you my new co-workers who are really rather good at ball games, and here you are, all right? And in fact, actually, I had to show you this one. This is Joe Namath, okay. When I was here in the 60s, I was a big fan of Joe Namath. I would say the greatest quarterback I've ever seen. Because he could throw the ball. He threw the ball most of the time, and most people don't throw the ball now. And my favorite story about him is that Joe actually went down to the Houston Astrodome when the Astrodome was new, and they had artificial turf. And he sort of said, after the first game on artificial turf, he said, well, Joe, do you prefer AstroTurf or grass? He said, I don't know, I've never smoked AstroTurf. So, he's in New York yet too. Okay, there you go. Okay, there but anyway, I thought I'd show you my group, a fantastic young bunch of students. There's Steve Aqua, whose parents are from Ghana, Daryl Ventura, Artri Span, Prashant Jain from India, Nicola Pugna, a guest from Italy, and Paul Dunk. And the guy in the top here is actually Paul Dirac, who sits out in the sun most of the time, so I put my hat on top of him to keep him a little bit of the shade. Paul Dirac actually spent 13 years at Florida State. I'm working at the moment, I think I'll tell you a little bit of what we're doing. We're working on things like C28, okay, smaller fullerenes, because it actually behaves like a superatom, and it's actually it's a tetravalent superatom. Not only that, titanium C28, okay, is here. We've found that where we can produce a titanium atom inside C28 when there's no C28 at all. And we're doing that by mass spectrometry. And here is the C28 molecule where all the electron density is focused on one particular structure. I thought I'd show you this. There's a lot of things I could show you, but this is really quite interesting. Give you a bit of an idea of the sort of experiments we're carrying out. What we have here is a helium bath, okay? And here is a wheel, or it's really a rod, cross-section of a rod, on which we've put some C60. This could be a glass rod, or a graphite rod, or a carbon rod with amorphous carbon-13 on it, okay? Now then, what we do is we open and shut that valve, helium passes down, we vaporize what's on this wheel, and down here we look by mass spectrometry at what's happening. Okay, let's do it again. Open, shut, pass down. Let's do it slowly, okay? Open that, pass down there, fire the laser, and what happens is that the laser evaporates C60 from this wheel, and we can see the spectrum of C60 by mass spectrometry. It's a laser vaporization technique. If we put this on graphite, then we actually vaporize some carbon at the same time, some carbon atoms and C2 species, and they actually inject into it. Now here's the C60 coming off by itself on a glass rod, okay? Almost no decomposition. It's quite interesting. C60 comes off. There's the mass spectrum of C60. If we put it on carbon, we see that we can grow 62, 64, 66, all the way 70 and all these ones, okay? We actually can vaporize carbon, and the carbon atoms and C2 species inject into it. We can grow it. And here we see it on carbon-13. And if we grow this on, look in detail, this is the C60 signal. And I want you to look at the resolution we've got. Alan Marshall has developed ion cyclotron resonance mass spectrometry. We can measure the mass of any species in the system, okay? And if we look at this, these are carbon-13 species. This is C62, 64. We can grow C60, which is not shown here, all the way up to C100, in fact to C120, by injecting carbon atoms into these things. There are no C60 and C60 are not stable, yet we can grow those whole things on there. And so we've got a way of making larger fullerenes, which is a surprise to me. And it was Paul Dunk who actually did this particular experiment, okay? And we've shown that basically the fullerenes, in the way they grow, is that some sort of small fullerenes are made, and we don't know exactly how that, because it's a very complex process. But the second stage of that process is that C30, 40 are growing into C60 and the larger ones. And here, this is now a paper that's just coming out in Nature Communication. Here's Paul Dunk, who did this experiment. It was his idea. I didn't think it would work, but as you go, you know, it's really great to have students who do crazy experiments that you don't think are going to work, because then they show you that you're the crazy ones. That's the most important aspect of working in a university, that you work with young people who don't have your own hang-ups. And this is Alan Marshall, who's developed this fantastic Fourier transform, ion cyclotron resonance mass spectrometry. Okay, so what is nanotechnology? It's chemical self-assembly, okay? So what do we think about it? Would it be possible one day to create a computer by bottom-up chemical assembly? That's an interesting question. Well, look what has happened. Basically, that has been created by bottom-up assembly, which is a pretty complex system. And there's no obvious reason why we can't reproduce something similar at all. It's just a case of possibility. One thing is, let's take this as an example. One of my favorite objects is the old ferrite core memory. And in fact, it's interesting because it's very simple to understand how it works. You put half the current down one of these coils, okay, you put the other half down there. Half will not magnetize one of those ferrite coils, but both together will. So this is how the old ferrite core memories worked, okay? So we are now looking at this and trying to create two-dimensional layers of magnetic molecules, okay? And we've actually made these. We haven't got a mono surface or a single layer surface, but we have actually got that. And we're getting close. And if we can do this, we can reduce in one dimension, we can go down by 10 to the minus 7. And therefore, if we can produce by molecular assembly a set of magnetically detectable or sort of identifiable clusters, we can put 10 to the 14 of these where we now once had just one of these ferrite cores. So that's the sort of things we're trying to do. Of course, you can never keep students down, and so instead of doing he made those two-dimensional ones, and he went on to three-dimensional ones, too complicated for me. But let's look at this structure, okay? It looks a bit complicated, but let's simplify it. It's actually 8 zinc atoms, surrounded by oxygen, linked together by a formate group with a methyl ammonium atom in the center, okay? Now, if you look at this in the center, you see that there are 3 positions for the nitrogen, which is a bit odd. But what is actually happening is really quite fascinating. What is happening, the nitrogen is jumping between these positions, and in fact, you can get it to rotate. We're producing a functional ferroelectric material, and we can orient the nitrogen by putting electric field on the outside. And here is Prashant Jain, who did that work, and it's done with Naresh Dalal and Tony Cheetham. Got to now say something about where I think exciting areas are. If we think about penicillin, now this is a miracle molecule, okay? No praying needed, this works, okay? Okay, blood poisoning in 1942. In 3 weeks, this kid was cured, all right? That is an amazing thing. And here is the person who really did all the work. How many of you have heard of Norman Heatley? 1 person, 2 or 3 people. This is the star. Didn't get the Nobel Prize, but he is the star of that piece of work. But the problem is that bacteria are evolving with an immunity to antibiotics. We could be going back to this, okay? That's the worrying factor. And we need young people to actually sort that sort of problem out. Nitrosoethane is actually my favorite molecule. You might think it's C60, but it's not. It's this one. Does it look like anything to anybody? That's right, it's my dog. Kind? Red nose, dog. I look at the microwave spectrum, I know the dog shakes its head, okay? All right? And it looks at its tail. Not only that, this dog can do a lot of little tricks, okay? As good dogs can. First, the hydrogens can undergo internal rotation. It's been drinking, it's an underage sort of drinking dog, got a red nose. And if you've been drinking too much and you're a dog, you know you're in the Bronx, what you desperately need is a lamppost so you can use it. Okay. That's the dog. Now, the reason for showing is everything I've shown you, this molecule actually does, okay? It's flexible. And my view is that the future is going to be molecular machines and recognize that penicillin is a fantastic molecule, but it doesn't do what this molecule. This is hemoglobin, molecular machine inside your body. Max Perutz showed this. This was the first molecular machine detected. Not only that, bacteria, as you know, have these fantastic irises. There's a paper came out 2 or 3 years ago that this is used to control water going into and out of the bacteria. And this, I think, is my all-time favorite piece of animation. This is ATP synthase. Now just look at it. These are protons here adding onto this negative moieties on this wheel and turning it around like a real electromotor, driven not by electrons, but by protons. And as it turns, a spindle inside here opens and shuts these cavities and lets ADP, adenosine diphosphate, in and phosphate together, and out comes ATP. Now that's a catalyst, 100% catalyst. And I'm just thinking, you know, it takes me back when I was a little kid with my Meccano motor, okay? And I would just think, today's kids working in molecular biology and these areas have got these fantastic machines to work with. If you can't get excited by that, then go and do something else, okay? Because that is some hell of an amazing system. And certainly I would like to work on it. All right, a few points. Now I get to a bit of a serious point in my talk. It's called science lost in translation. The real problem is what is going on today. As you well know, science is coming under a lot of criticism. And what are we going to do about it? And I like quotations, and I say, I seek not the answer, but to understand the question, what is going wrong? Because I think if you start to understand the question, the problem, maybe we'll get towards an answer. And I thought I loved this quotation so much that I better go to Google and find out who actually where it came from. So I put this into Google, okay, and what I discovered that it was me. I'd said it so often that Google decided that I was the originator of this thing. But if you actually say, I seek not to know the answers, but to understand the questions, then it's kung fu, right? So that's pretty good for me. Okay. Now, what do I think? I think that chemistry, molecular biology has given fantastic contributions. And this is one of my favorites. There can be no more humanitarian contribution than the gift of anesthetics to humanity. This gives you an idea of what it was like to have an amputation. I want you to look at it to realize what it was like in the 17th century and 18th century to have an amputation. Women had a mastectomy without an anesthetic, all right? We have given some of the greatest contributions, and I think we don't get any credit for it, this scientific community. And that's the problem, okay? We have become part of the woodwork, so much part of the woodwork that people don't even think about it. And when they do, they think about science as only being something that's useful, okay? And this gives you a graphic picture. I wish they'd had mobile phones in those days so we could really see what goes on. We've talked about penicillin and other things. But what about the science pros and cons, okay? What would happen if we now go along this road and say, okay, we're not going to do any more nanotechnology, okay? We've got this anti-science aspect. Let's go back 100 years and say, have the same attitude to chemistry. Oh, chemistry, it might produce big dangers, and it does. Thalidomide tragedy, the Bhopal tragedy. Let's now say we're not going to do it because those are the risks that we have. If we'd had that same attitude that we have at the present moment to science, then there would be really bad things. But it seems to me the really bad uses of technology are those we can avoid because people are the atomic bomb was dropped. People are using technology, they're using airplanes they're using bombs and stuff like this. Isn't it unbelievable that in the 21st century we can't get rid of that aspect? But by and large, I think people would say science has provided great benefits. And if we think about chemistry and said, let's not do any chemistry 100 years ago, all these things would disappear. And in fact, physicists and biologists and engineers could say the same thing. And many scientists work together to solve big problems, look after the environment, improve world health, understand how things work, and enjoy making things. So these are some of the aspects that we need to think about. Okay, so I was talking about what science is, and I think it's totally misunderstood. The first aspect of science that one needs to think about is that it's a body of knowledge. It's what you learn at school. Okay. Number two is the application of that knowledge, technology. And the third is basically how is new knowledge discovered, the scientific method. Those are three pretty focused, easily aspects of sciences. However, I think there's something more important. And it's because science is so useful that people have forgotten that it's a cultural activity. It's an intellectual activity. It's something part of our culture. I would argue one of the most important to music, as important as art, at a cultural level. And politicians and others don't look at them. They think if it's not going to be useful, or if you can't make out it's going to be useful, or if it's not going to be useful, then it's not worth doing. But before it was useful, it had another name, and it was called natural philosophy. And the most important aspect, by far, is that natural philosophy is the only philosophical construct we have devised to determine truth with any degree of reliability. This is the most important thing I have to say as far as I'm concerned. So I'm going to say it again. Natural philosophy is the only philosophical construct we have devised to determine truth with any degree of reliability. I will define it as such, okay? And if that can be considered as a construct, then the ethical purpose of education must be to teach every child, every young person, how they can decide what they're being told is actually true. All right? You can't disagree with that. Or you can, if you wish. And so the teaching of a skeptical, evidence-based assessment of all claims, without exception, is an intellectual integrity issue. An issue that all teachers must address, especially in this country today. Without evidence, anything goes. Think about it. This is what I think is very important. Let's take an example. 3 senses. Common sense. Common sense says that the sun goes around the earth. Who agrees with me? That's what it happens, right? Where was it this morning? Over there? It's over there now, right? It is obviously going round us. It's uncommon sense that tells us the earth is turning on its axis. That makes it seem as though the sun is going around us. And until 1600 people, nobody, almost nobody, except 1 or 2 Greeks, 2,000 years ago, thought this was happening, okay? And this is interesting because it's the uncommon sense and bravery of Copernicus, Galileo, and Giordano Bruno. And Giordano Bruno was burned to death for one of the reasons was this. So these are brave people. You have the legacy of science and the freedom to do science because of these people. And so you have to think the way that they do. And if you don't, you do them an injustice. Because these people created the world, freeing you to look at it in a different way from everybody else outside the natural philosophy and scientific group. Most people have accepted the claim that the earth goes around them without knowing the evidence. How many know the evidence? 1 person. Very interesting. So you've accepted that the earth goes around the sun, or you've accepted that the earth is turning on without knowing the evidence. And that's a very important point that you need to think about, because what does that imply about you? What else have you accepted without knowing and checking the evidence? Many people accept claims for which there is no evidence whatsoever. Think about it. Science is different from all others. We learn that we must not accept anything without evidence, question everything, all claims without exception. Okay. And it may take millennia to overcome the power of unauthenticated claims of dogma-based authority. As an example, it was 1992 when the Vatican finally decided that Galileo was right. In fact, they spent 13 years sitting at a table deciding on this. Okay? Because this produced major problems for this group of people. So one of the reason I'm here is because I want you to think about this issue, okay? Okay, oh, I really want to go back because there's one other thing. There's one other sense. It's called nonsense. And nonsense is common, and you can hear it every day on Fox television, okay? There's another issue of heroes and heroines. This guy's thought to be a famous scientist, you know, and the problem is that he's an imposter. He didn't do all those things. Everybody thinks that that was the guy who did the theory of relativity and the photoelectric effect, and it's not true. It was this guy. Totally unknown. Okay, yes, it was young Einstein. In fact, it turns out that basically this was the guy who did it. Because at this point, he was formulating his ideas, and he was wondering what it would be like to travel at the velocity of light. It's young people who actually build an understanding. Old guys like me, we're way past it. Darwin, this book changed our views. Whether you accept it or not, I don't care a shit. All right? Because there are people who don't. When the evidence comes from every part of the sciences. The attack on Darwin is not an attack on Darwin. It's an attack on the scientific community. And don't underestimate that attack. Because the evidence for this book comes from every part of the sciences, from geology of tectonic plates drifting apart, from physics of radioactive decay, from chemistry, from geology, from paleontology. There is not an area where it doesn't fit pretty comfortably with this, okay? But he was a wee child, a young child, 24 years old, okay? Clerk Maxwell is responsible for the most important breakthrough of the 19th century, these 4 equations, Maxwell's equations. Every time you use your mobile phone, you prove that those equations are correct. All right? That's fantastic. The millions of people are proving this equation. That's what science is. It works. Nothing works any different. Well, when he created that amazing set, here, it's wee Jamie with a little quiff on his eye. He's a Scotsman, right? The Scots are incredible. I mean, this guy basically is responsible for electromagnetic theory. James Watt, a Scotsman, invented the condenser, which was the start of the Industrial Revolution. And the greatest philosopher was probably David Hume. Okay, I hate to say this because my wife is basically Scottish, but I'll give her. But there you go. We Sassenachs, but you know, my parents were from Berlin, so I'm not quite a Sassenach. Amazing what these three people achieved. Hume, the greatest doubt-based questioning philosopher of all time. Wee Jamie, Maxwell's equations, electromagnetism, and Watt, who didn't invent the steam engine, but with the condenser made it efficient. And that was the start of the Industrial Revolution, which may or may not be a good thing. Rosalind Franklin, this beautiful lady, created the most important photograph, took this photograph, the most important photograph of all time. This X pattern indicated that it was a double helix, and this missing line here indicated the sets. This is incredibly simple picture, but the most important photograph of all time. Led to the structure of DNA. Chandrasekhar was a young man when he realized that a star 1.5 times the size of the sun would collapse into a neutron star. And young people like Jim Heath, Sean O'Brien and Yuan Liu and Jonathan Hare were the students who helped us with our discovery of C60. Now there are students who really are very interesting, and I thought I'd show you this, okay? There you go. This is the Dirac equation, and there's the Hamiltonian equation. Now there's an error here, right? There's a minus sign. I have been through this equation here, so that he should get his money back from the guy who, but he probably can't see it, you know. Maxwell's equation, DNA, the Heisenberg uncertainty principle. I'll cross that was LSD, just in case you want to make. My favorite is this one. Now just listen to what Nicole says. Nicole, a physics graduate student, my tattoo is Taylor expansion of sine. I consider it the most beautiful thing I have ever learned. It has the additional meaning to me that since sine x is equal to x, is one of the most useful things in physics. It's one of the most beautiful things, piece of mathematics is concerned. I just like that very much. I do kids workshop all over the world, okay, for small kids, okay? And here's in Japan, Santa Barbara, Malaysia, via internet to Iceland, over Australia, in the UK. Oh, when I show this picture, young women in England go screaming. It's not me, it's the guy who's got the hair, actually, over here on this end. Which is, he got the golden boot. He was playing for Manchester United at the time, but he was the top footballer in the last World Cup, Diego Forlan. And here, this is my favorite guy because he's the first guy to find a use for C60. Okay, there you go. Young people really do everything. But I want to tell you something about your world which is so different from mine. And it's this. How many of you have looked at an encyclopedia? This week. All right, there we go. All right. Now then, what is different? It's called, what I call it, the GUI wiki world, okay? These and the other companies have transformed the world, because here we see an image in Encyclopedia C60, not that imaginative, but if I go to Google Image Browser, put in any of those things, and what do? I get pages and 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 even rotating buckyballs, okay? You have something that I could only have dreamed of as a kid. Triple revolution, finding it, making your own movies, and Wikipedia, the passion to create this. These are three major contributions to the knowledge base that you now have. And we are now creating a new one, okay? And I hope you're going to help me here. It's called GeoSet. So what are we doing? Well, I don't actually need to be here. In fact, last weekend, I went to Egypt and to Singapore by the GeoSet project. We have a capture station. Basically, this video is in here, and there I have the PowerPoint. And I could come by internet. And I'm doing this now all the time. I shall be sort of recording one next week to go to Stockholm in 2 or 3 weeks' time. And in fact, they're synchronized. The future of broadcasting, as far as I'm considered. Okay, there you go. Okay. It's called Geoset, and these are two of the websites. This is the gateway site, geoset.info, and that's the FSU site, but we have other takers. And I'm going to show you one or two of this. This is a graduate student.
Hi, my name is Kerry Gilmore, and I am a graduate student here at Florida State University. I work with Dr. Alboon as the organic chemist. Now, I love organic chemistry because it provides the opportunity to go through and be an architect, an engineer, builder. We can go through, we can really look at designing molecules, we can figure out how to actually make these molecules, and then finally, we actually get to go in the lab and actually build these things. Now, the greatest organic by far is nature. Nature can go through and take something as totally simplistic as these small seeds, and through a series of organic transformations, using chemistry that we ourselves use, it will go through and transform into these beautifully complex and beautiful flowers that you can see here. Now, what we do is much the same. We'll take something relatively small, something relatively simplistic, and through a series of transformations, we need to figure out how to make something that's much larger, much more complex.
I'm going to jump on.
If we were to add more triple bonds in this case, we could go through and fully zip up these structures. We could go through and take something, instead of just something that's relatively small, and close up. We can extend that all the way through and form much longer chains. And
I'm running out of time, but I want to show you some others. That's a graduate student. And this is, let me just go on to this one. This is an amazing story.
Recently, the first case of inbreeding that was scientifically linked to deformities in animals was released. This study was done by John Buchetti and Ralph Peterson with the School of Environmental Science at Michigan Technology University on a population of wolves, a very close relative of the dog. The study was conducted on a small, isolated wolf population located at Isle Royale National Park in northern Lake Superior, Michigan. The 3 cats are comprised of around 24 wolves, all descended from 1 female and 1 or 2 males, who crossed an ice bridge from Canada during the unusually cold winter in the 1940s. Since then, they have been isolated on the islands that make up the Isle Royale National Park.
Now I'm going to just stop there.
In this population of 24 wolves.
Just let me stop there. This is an amazing story. This bunch of wolves, it can never repeat it. You can't set it up. They've been trapped for 70 years, so it's a fantastic study in inbreeding. I'm going to jump on, so just wait a second, because I'm going to jump on to the results, because she's now found this paper.
The photograph on the left-hand side is what a normal wolf vertebrae should look like. And this photograph on the right is a defective vertebrae. Again, in this photograph, you can clearly compare and contrast the...
Let me just go on.
This graph shows the vertebrae defects in relation to the estimated birth date of the wolf. The number of deformities seemed to increase significantly during the late 1980s. Buchetti and Peterson noted that for the last 12 years, every one of the wolves they found dead had some sort of bone deformation.
I'm going to jump on now to what she says.
Part of my motivation for choosing this topic is my love of animals. I want everyone to be aware of the atrocities that occur at pet mills. These facilities are guilty of overbreeding, inbreeding, minimal veterinary care, poor quality of food and shelter, lack of human socialization, overcrowding of cages.
I'm going to stop it there. This is part of her resume, okay? This is a really effective part of it. I'm going to jump out of that because I want to show you that these kids are actually doing. This is by Steve Aqua, whose parents are from Ghana. I brought Steve out with me to help me with my group.
Today, I'm kind of in disguise. I had a meeting with Agent X, and he gave me a secret document. Real? Top secret. Now, the problem is, he gave me all this information. X, right before he disappeared, gave me these 2 envelopes, A and B. Now, according to him, it contains a secret message. secret message written in invisible ink. Okay. Well, luckily, he told me that he wrote the instructions down and put them in envelope B. And unfortunately, that also seems to be written in invisible ink.
Never mind though, we can work this out with a bit of chemistry.
So, what will we need for today's experiments? Well, firstly, we'll need some kind of heat source. I'll be using a heat gun, which looks somewhat similar to a hairdryer. But anyway.
I'm going to stop it there. This shows you that our kids can be really imaginative if you give them the opportunity with modern technology. And we're just creating a website with all this information on it. And I set this up to create educational material, concept modules, not whole lectures necessarily. But what we've done is we've revolutionized the resume. Because instead of being, at that point, a pile of arid paper where someone has to spend, afternoon reading this bloody stuff through, we can put you on top of the pile, okay, which is there, and we can give you an idea of who you are and show you young people how you can show yourself off to the best. And here is the evidence, because I'm an evidence guy. Kerry, who you've seen, got a Fulbright. Steve, I asked him to put together something on our GeoSet program, and we got a Rich Media Award. Prajna got 4 tenure-track offers, and they told her at one place, we could see from GeoSet you can teach. Brittany got into medical school, said that GeoSet presently was the defining factor in getting into medical school. Jeff said it was fun to do it, and I think it helped me get the position. Arteries, this is interesting, Arteries is one of my students, and she made a recording, and she sent the URL in her application, and when she got there to the interview, they'd already seen this, and they said they enjoyed it. So she'd already was 90% of the way there before she had the interview. Vinny, you haven't seen it, but you've seen a bit of Jennifer. Jennifer, 3 or 4 weeks ago, wrote to me and said, I got into vet school, which is what she wanted, and it's damn hard to get into vet school. Mark Riley, my physics colleague, said the URL links were sent to our NSF funding people, and they were very impressed, and the committee who reviewed the grant thought so too. It's actually, there's nothing that it isn't positive for, okay? And in fact, some of you know what it's like to do an assessment. You've got to do some marking on Saturday afternoon. In my case, I get my students to do a presentation, and instead of marking them, I watch them in my home in England on the internet, drinking a glass. And here Margaret took this photograph of me drinking a glass of wine. It's a pleasure to mark this, to assess the students. Within the next 2 to 4 years, it will be de rigueur. You will not be shortlisting assistant lecturers that you want without having seen them on the internet. It's inevitable. And it's coming very soon. And last week, some of you will know, MIT and Harvard got together. They're going to record a whole load of their undergraduates. They haven't fully realized that this is what we've actually done for the last 2 or 3 years. And we're setting up GeoSet nodes. They're all over the world at the present time. We've got material coming mainly from Florida State and from University in Sheffield, but also from Japan as well. In fact, an Indian student at Toyo got her job back in India via the internet because she made a recording, and she's now a professor back in India because of that. And Steve Aqua, Sam is where he's a TA. I think he wants to be on Baywatch actually in this particular picture, and Colin and Penny are the people. And Margaret here is responsible for me getting here. She usually decides, well, she gives me advice as to where I should go. Okay. Attitude, if I have anything, it's not to do with being smarter than anybody else. It's because that I just never do anything second rate. I do the best I can. You can do better maybe, but I always give things the best shot. Second rate effort, I'm not going to do it. If I'm going to do second rate, I'm going to let someone else do it, okay? But I have to satisfy myself, not a teacher or somebody else. And so basically, I would say that if I'm here by any other reason, it's because my attitude is I never did second rate stuff, but I never knew what I was doing, okay? I mean, like, from The Lord of the Rings, not all those who wander are lost, okay? Now that sort of sums up me. Okay, Ines, I think if you're a scientist, I think you have a responsibility. And you have a responsibility as a physicist not to make any more atomic bombs. If you're a chemist, not to make any more napalm. Let's try and get rid of it. And if you're an engineer, no more landmines. I think those are things that I think are responsibility. And finally, the last few minutes, outer space, from basically nanotechnology and in outer space. The Third Man. One of my favorite films is The Third Man, Der Dritte Mann. How many of you have seen this film? Yes, everybody over a particular certain age. Okay. I always thought of C60 as the third man. Diamond and graphite have been known for millennia. It's an amazing fact that it took till the end of the 20th century to discover the third molecular form, but that was the case. It was hidden, it was hiding, it was there. We should have seen it. We should certainly have seen it in the 60s because it occurs in combustion, in flames. It was missed. Some people said, there was fleetingly. It was like the third man, like Orson Welles, lurking in the back streets of Vienna. And I always thought that C60 was lurking in the back streets of the galaxy. And here's a bit of film.
What kind of a slimy thing you are, Snagglefoot? What are you tailing me for? Cat got you down? Come on out. Come on, where you are. Step out in the light, let's have a look at it. Who's your boss?
I'm going to stop it there. You can watch the rest on YouTube. Oh, some of it on YouTube. How many of you know that film? Just a few. Fantastic movie. It's a cult movie. And there's this character, Orson Welles, who people think is there, and it's just like C60. And I thought, well, he was lurking around. And then, over a year ago now, some amazing results came out. This NASA Spitzer telescope came up with this spectrum. Now, the white spectrum is the spectrum of a star, okay? Now, look at these peaks here. And the red is the spectrum of C60. And the blue is the spectrum of C70. All the peaks are there. Now, this is incredible. This indicates we really don't understand very much about carbon. Because this is the infrared. This is the fingerprint region. We've got the fingerprints of thousands, millions of molecules, and yet there's almost nothing else identifiable coming out of this star, out of a chaotic plasma of some kind. So there's something very unusual about this star and several other stars where this molecule is discovered. And it's really fascinating that here is C60, as I always thought. And I really did think that as we'd simulated the conditions in a star and discovered C60, it must be there. But I never, for a moment, thought it would be so easily detected and so easily proven. And in fact, basically, that's the situation. I thought I'd show you and finish with this bit of film from the BBC in 1992. This is Wolfgang Kretscher, a great guy. And this is with Hoffman and students, Loyal Lamb and Kostas Fosteropoulos. They extracted C60. Okay. Anyway, this bit of film is at the last few moments of this film.
I believe it is there, and it would be rather nice to feel that in fact we were on the right track. There are some interesting features in space, and C60 certainly can fit in better than any other proposal that's been made up to now. I'm a believer, and I think ultimately we'll find it is there.
But others have said that C60 is nothing like a match with the people so far.
They're wrong.
Thank you.